Okay, it says esters are difficult to distinguish from each other using chemical test. So NMR spectroscopy is often used. So there are four esters isomers with the molecular formula C4H8O2. Their displayed formula shown. So we have four esters. Explain which of the four esters can be distinguished from the other three by the number of peaks in C13 NMR spectra. Justify your answer by labeling any equivalent carbon atoms. When you look at this one, so in C13 we are checking the number of carbon environments. So if you take this one, so this is the first environment, carbon environment for this molecule. So we have the second one, we have third one, and we have fourth one. So this one has four carbon environments. And if you go from this one, this also have four. 1, 2, 3, and 4. Okay, this one also have four types of carbon. This one also have 1, 2, 3, 4. 1, 2, 3, 4. But if you go for this ester S, you can see this is one environment. This is the second environment. But if I look at these two carbon atoms, their environment is similar. How do I know it? So remember, if you see a structure like this, there's a structure, and on the same carbon atom, there are two, like that means we are talking about secondary type of structure. If you have in the same carbon atom, you have two carbon atoms attached, and both have same type of atoms attached around it. So there's a very high like probability these two carbon atoms are in the same environment. So that means this one and this one, they are in the same environment. So same scenario we have here. One carbon atom is there, two carbon atom, both of them has hydrogen atom. Why they have draw the structures in two different, then you get confused. But if I take this carbon, I will take the first one. Okay, if you take this one, you can say that this carbon atom attached to a CH group, and that CH is attached to a CH3 group. And from the other side, the CH group attached to a oxygen and COH group. Let's talk about this carbon atom. This carbon is attached to a CH group. That CH group attached to a CH3 group. And that CH attached to O, COH. You can see that the same story. So that means these two are the same environment. That means this ester S and only has only one environment. So that means you have 1, 2, and 3 type of carbon. All these three molecules will have 4 types of carbon. But because this one has only 3 types of carbon, you will see 3 peaks on the esters. So the marking point says that esters can be distinguished from the others with 3 peaks. In C13 NMR spectrum, the other 3 esters have 4 peaks. So therefore you have to show this one. So the marking points, these are the marks. You have to say that esters has 3 peaks in C13 NMR. Other 3 have 4 peaks. That's the second mark. Third mark is labeling for it. That means you have to show the environment. You have to show that in this one, these two carbon atoms are in the same environment. Or you have to like at least number them. Somehow you have to show that that environment are same or they have only 3 carbon environments. Right, in part B, it says that there are 9 ester isomers with the molecular formula. There are 9 ester isomers with molecular formula C5H10O2. The displayed formula of 2 of these esters are shown. Now the way they have given 2 of them, W and X. Ester W and X both have one peak with a relative area of 3 in their raw resolution proton NMR. Okay, they have, okay, we have to understand that part. Both peak with a relative area of 3. Both have one peak. Okay, both have one peak. So I think this is that one peak they are talking about. One peak. So in the proton NMR spectrum, SW both have one peak with a relative area of 3 in their low resolution proton. So that means there's a one. A singlet means in the adjacent carbon there cannot be any hydrogen atom. This is one thing you have to understand. If you have a proton environment, so let's take this is proton environment. The relative area tells you how many protons in that environment, how many hydrogen. Proton means hydrogen. Proto 3 means there are 3 hydrogen. And this one peak means in the adjacent atom to this carbon, if there's adjacent carbon, there cannot be any hydrogen. So there is no hydrogen in this adjacent carbon. Since there's no hydrogen in this adjacent carbon, this peak. So here when I look at this one, there's no adjacent carbon, right? Which means there cannot be any like sub peaks for this one. And if you take the next one also, this one also have one environment with 3 hydrogen, and in the adjacent carbon there's no hydrogen. So that means these two are the singlets you can have, right? Explain how these peaks can be used to distinguish these two esters. So how we can distinguish is, if I take this peak, if you look at the data booklet, this carbon atom is attached to oxygen atom. That means you have to find an hydrogen environment which attached to a carbon atom which directly attached to oxygen. So if you refer your data booklet, you have to find something like this, HCO, this peak. If you refer the data booklet, you will get this peak should appear between 2.8 to 4.2 ppm. But if you take the next environment, the environment that we are searching there is a hydrogen atom attached to carbon, where that carbon is attached to a carbonyl group. That carbon is attached to a carbonyl group, right? So therefore, if you take the data booklet for this peak, it will be between 1.6 and 2.8 ppm. So you can see those two peaks are appeared in two different locations. Since they appear in two different locations, we can easily identify that what it says. The peak for SW, this one, is a chemical shift range from 2.8 to 4.2 ppm. That's the answer we are writing here. But peak for X to X is appeared between 1.6 to 2.8 ppm. That's how you can distinguish them. Then if you go for part 2, the displayed formula for two different esters are shown in the boxes. We have another two, Y and Z. Label the displayed formula for two esters Y and Z to show the proton environments and the splitting patterns of the peak in the high resolution proton NMR spectra. Clearly indicate any equivalent proton environments. For any multiplet, you may refer to the number of separate peaks in the multiplet rather than giving a name. Okay. You may refer to the number of separate peaks. Okay, let's take this one, ester Y. In high resolution proton Y, it tells you the number of peaks means are types of hydrogen. One, this is the second type of hydrogen. This is the third type of hydrogen. This is the fourth type of hydrogen. And this is the fifth type of hydrogen. So you have 5 types of hydrogen there. So we are talking about peak number 1, peak number 2, peak number 3, peak number 4, and peak number 5. And if you take the sub peaks, in peak number 1, there's no any hydrogen attached to adjacent carbon. So that means there's no any adjacent carbon also. So that means this will remain as a single peak. If you take peak number 2, in the adjacent carbon, there are carbon environment is there. So adjacent carbon, this one has 2 hydrogen. There's another hydrogen, that will be 3. So 3 plus 2 is 5. So we know that there's something called n plus 1 rule. So this will be 5 plus 1 rule. So this one will become a sextet. That means there will be 6 sub peaks. Peak number 3, adjacent carbon has only 1 hydrogen. So therefore, this is the adjacent carbon. It has only 1. So it will be n plus 1. That means 1 plus 1. So it will be a doublet. If you take peak number 4, adjacent carbon, this side there's 1 hydrogen, this side there are 3. 3 plus 1 is 4. So we are talking about 4 plus 1. So this is will be a pentlet. And if you take peak number 5, adjacent carbon has 2 hydrogen, 2 plus 1 is 3. Now that means this will be a triplet. So we know the peaks, and from their adjacent carbon we can tell about how many subpeaks we'll get. So this is the environment. So this is A. If I take them A, B, C, D, like let's go change their names from A, B, C, D. So this is environment A. This is environment B. This is environment C. This is environment D. This is environment E. And if they ask relative heights, relative area, or do they ask about relative area? For any multiplet, you may refer. Label the displayed formula of the two esters Y and Z to show the proton environment and the splitting patterns. Okay, they are asking proton environment and splitting pattern only. 1, 2, 3, 4, 5. 5 environment, this is the splitting pattern. Singlet, sextet, doublet, pentlet, and triplet. If you go for next one, this is my environment A. This is my environment B. This is my environment B's two hydrogen protons are there. This is my environment C. These two, can you see again? We can see the secondary type option. One carbon is there. Here we have CH3. And here also we have CH3. That means we are talking about the same look like the similar like environment. So that means we can assume both these 6 hydrogen, they are in the same environment. But they are drawn in a different way where it's hard for you to recognize them. But we can recognize now we have environment D here. Okay. Now in this one we have only 4 environment A, B, C, and D. If we take environment A, in the adjacent carbon there's no hydrogen, so therefore there's no adjacent carbon, there's oxygen. So therefore this will be 0. So 0 plus 1 is it will be a singlet. And if you go for environment B adjacent carbon there's 1 hydrogen, so 1 plus 1 is 2, so then it will be a doublet. If you go for environment C, adjacent carbon have here 1, 2, 3, 4, 5, 6, here 7 and 8. 8 plus 1 is 9. Okay, 9 subpeaks. If you go for environment D, adjacent carbon has only 1 hydrogen, 1 plus 1 is a doublet. So 1 plus 1 is a doublet. So we have 4 peaks. This is the splitting pattern. Now let's go for our answer and see. Yes. First one we have singlet, sextet, doublet, pentlet, and triplet. Yeah, that's correct. Second one we have singlet, then doublet, then nonet, and we have another doublet. Yes, what we did was correct. So that's what they are expecting. Either you can write the singlet doublets, the words, or either you can show it using this subpeaks. You can tell the number of subpeaks. Right. So that's one thing you can do here. So it's better you draw, they ask you to like draw the displayed formula using the displayed formula, explain it clearly, right? That's what they ask. So 4 marks are given. So they are expecting an answer like this, right? Correctly label in the environment, circling them is better. Then you tell you how many subpeaks are there, right? Then draw the displayed formula of the C5H10O2 ester which has only 2 peaks in its low resolution proton NMR. So when you have ester, only 2 type of environment. So obviously that means, now when you look at this one, we have 10 hydrogen. So there's a best way to put 9 hydrogen in one environment. You can remember this one. So we know that if you go for tertiary format, in a tertiary format, when you place them like this, so you can see that all these 3 CH3 group attached to the same carbon. So you know that this carbon atom should have a one environment. So that means without knowing, I have made all these 9 hydrogen atom in one environment. Since they have only talk about 10 hydrogen, the best way to put 9 of them in one environment is this one. So I just put all these 9 in one environment. Then problem is almost done. So this ester has 5 carbon. Already I have 4 carbon. So that means straight away I have to start the ester bond because I have already used 4 carbon. So this is oxygen. This side we have the carbonyl part. Okay, now I have put 5 carbon and one more hydrogen. That environment is the other one. So now we have two environments. So remember, when you are putting many hydrogen atom in one environment, when you put them in secondary phase or like in a tertiary structure, then you can get many hydrogen in the same given environment. If you go for question number 18, this question is about reaction kinetics. Halogenalkenes are hydrolyzed by aqueous alkali to form alcohols. Okay, for an halogenalkene, when you add aqueous base, the OH minus sign will replace this halogen atom and you get an alcohol. The rate equation for these reactions with two halogenoalkanes are shown. One bromobutane rate equation is now remember in a rate equation what appears on the rate expression is the reactant which are taking part in the slower step and how many of them. Explain how this rate equation can be used to deduce the different reaction mechanism of the reaction of hydroxide ion with these halogenoalkanes. Right. First I'll use this empty page to explain what's happening. 1 bromobutane and 2 bromo 2 methyl propane. I'll take 1 bromobutane first. Okay. So 1 bromobutane, and it shows that is and 1 in 1 bromobutane both reactants are taking part. This is what happens in 1 bromobutane. Okay, so this is the carbon atom. This is called SN2 mechanism. For 1 bromobutane we have SN2. S means substitution, N means nucleophile, 2 means the overall order of the reaction. So in SN2 mechanism, okay, we have bromine atom attached to the butane molecule, 1 bromo. So in the first carbon we have the bromine atom. So all the other 3 carbon atoms are like attached. So if you take this part, I'll put it in butane. So there has to be CH2, CH2, CH3. And there's a hydrogen atom here, and there's a hydrogen atom here. What happens here? Because this halogen atom is more electronegative, electron pair is attracted towards that. So this will become minus delta. This will become plus delta. When OH minus sign sees this plus delta on this molecule, OH minus sign can easily attack it. So OH minus sign oxygen atom uses electron pair and attack to this carbon. When it attaches that carbon, carbon and oxygen will form a bond. Since carbon cannot have a bond with 5, carbon cannot have 5 bonds. Now when this oxygen comes, it will be 5 bonds. So it has to let this one of this bond goes. So electron pair in this bond will be taken by bromine atom and moves away. And therefore what you get here is, now we have the carbon atom, now the oxygen atom is attached to it. OH group is attached to it. And you have hydrogen. And this is CH2, CH2, CH3, and the bromine atom is gone as Br minus sign. Right. You can see that in this mechanism there is a one step. And in that one step, both reactants are taking part. That's why we said, so when you have only one step in this mechanism, that's the slower step as well as the fastest step. So rate determines by the rate constant time, number of reactants taking part in the reactants taking part in the slower step. We have OH minus sign taking part in the slower step and one of it. And we have the halogen. So we have CH3, CH2, CH2, CH2Br, and that's also one molecule yet. That's why the rate constant. So rate equation tells you what are the reactants taking part in the slower step and how many of them. So since it's a nucleophilic substitution and the total order of this one is 1, order of this one is 1, 1 plus 1 is 2. Therefore, is SN2 mechanism. Right, let's go for next one. They said 2 bromo. That means second carbon we have the bromine atom. 2 methyl propane. Okay, they have 2 bromo, 2 methyl propane. The rate equation, there's no OH minus ion there. So that's what we call SN1 mechanism. In SN1 mechanism, what happens? 2 bromo is butane, but like with the 2 bromo. So it's like second carbon, there's a bromine atom. They say 2 bromo, 2 methyl. And the second carbon, there's a methyl group also attached to it. Okay, we have methyl group, CH3, and it's a propane. So this is also CH3. Okay, now we are going to talk about the mechanism of this one. For easiness of understanding, I just change the position of the bromine atom, then I can easily show it to you. So I put that CH group here, and the bromine atom is here. Right. Now, just like in this case, now obviously this bond is polar. The plus delta and minus delta is there. But the now OH minus ion cannot approach this carbon atom. The reason is they are steric hindrance. These CH2 groups are bulky. But that problem wasn't there for this hydrogen because hydrogens are very small part. So therefore this OH minus ion can easily go and attack to that carbon atom. But here it's not easy. Because of this bulky group we call it steric hindrance. Because of this steric hindrance, now our OH minus ion can't go and attack that carbon atom. Therefore what will happen? First we have to break this halogen atom out. We have to get some space where OH minus ion can come. To get some space, what will happen? Because of this plus delta and minus delta charge, this carbon bromine bond will break. Bromine will take both electrons and will move out. That's the step 1. And step 1 is a slow step. Why it is a slow step? Breaking a bond makes a molecule unstable. Therefore, it's a very slow step. But even though it's unstable, why they break it? Because when they break it, now our carbon atom will have positive charge. When you have positive charge, we call it is a carbocation. But this is a tertiary carbocation. Why it is a tertiary carbocation? We have 3 CH3 group attached to this positively charged carbon. And because of that, we know that CH2 group can push electrons towards the positive charge carbon. We call it inductive effect. Because of that, this tertiary carbocation is stable. That's why this method cannot be performed in the first mechanism. Because it doesn't have tertiary carbocation even if break without the OH. That's why they have to wait till OH minus ion comes and form a bond. But here not a problem. We just first let Br minus to go out. Right. This is called intermediate. So we get the intermediate. Now we don't need to worry about the second method, step 2, because we can see that this is the slower step. Rate expression represent the particles or reactant which are take part in the slower step. Slower step, I don't have many particles. I have only one component, that is this tertiary halogenoalkene. So I have tertiary halogenoalkene CH3, 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 Br, only one molecule of it. That's why overall load is 1. That's why we call it SN1. Let's see what happens after this. In step 2 is a fast one. Because now our intermediate is unstable. Now it wants to neutralize this OH plus charge. So therefore what will happen in the second step, in the fast step, our OH minus ion will get attracted towards this intermediate carbocation. CH3C, CH3, CH3, plus charge is there. Our OH minus ion will come really fast using its electron pair. So it's an attraction between plus and minus. So this reaction will be very fast and you will get the alcohol. So those are the things we have to discuss. Now we'll go back to the question. So when you see the question, we will see what are the things we have to write. So that's the theory part behind this mechanism. So if you go for the question on this one, they are saying Question is about reaction kinetic. Halogen alkanes are hydrolyzed by aqueous alkali to form alcohols. The rate equation for this reaction with two halogen alkanes are shown. Explain how this rate equation can be used to deduce the different reaction mechanism of the reaction of hydroxide ions with these halogen alkanes. That means we have talked about rate expression tells you the number of molecules take part in the slower step, the reactors which are taking part in the slower step it represents, and how many number of molecules. That's what it represents. Okay, let's see how we can write the answer. And these are like indicative point mark question. When you see a star sign on top of the question, that means it's an indicative mark. That means if you write all 6 points, you get only 4 marks. The how your answer is like logically structured, that's where you get the other 2 marks. So that's one thing you have to remember. So let's see what are the 6 points they are asking. Only one bromobutane has the hydroxide ion in the rate equation affecting the reaction rate hydrolysis. So we can say that one bromobutane has OH minus ion there because it's OH minus ion taking part in the slower step of the mechanism. One bromobutane react by SN2 reaction mechanism. Now you have to talk about the reaction mechanism. So we discuss when you are drawing those structure, we say that first one is SN2 mechanism, other one is SN1 mechanism. If you have mentioned about them, you get 1 mark. And we have to talk about the hydroxide ions is only in the rate determining step. So you have to tell that rate determining step is the one the reactants over there will only appear in the rate expression. So in 1-bromobutane, hydroxide ions are there in the rate determining step or the slower step. So 1-bromobutane is react in single step via transition state. So we talk about that one in one step mechanism. 2-bromobutane forms a carbocation in the intermediate step. The hydroxide ion attacks in the carbocation. So that means if I draw that mechanism and I explain it using words, then I get marks because I discuss what is SN1 mechanism, what is SN2 mechanism there. I talk about rate determining step, slow step. Then and there's a transition state. 1-bromobutane reacts only through a transition, but intermediate step carbocation is there in the 2-bromo-2-methylpropane. The hydroxide ion attacks in the carbocation fast in the second step. So if I talk about those things, then we will get marks. So we'll write a sample answer. So when you write the sample answer, you will understand how we can use these 6 marking points uh, in logical order. Okay, so this is the sample answer. So you can write in rate equation. I can write in rate equation reactants take part in the slower step step will appear on it, and their number of molecules. Then you write the first one, 1-bromobutane undergo SN2 mechanism. SN2 mechanism means substitution of nucleophiles where total load is 2. Then you can draw the mechanism. So you can show the 1-bromobutane how it undergoes SN2 mechanism. We have bromine atom here. Then you have CH2, CH2, CH3. So we have hydrogen here. Then you have hydrogen here. Then you can show them OH minus sign there. And you can show that OH minus sign directly attacking this with plus delta minus delta. So OH minus ion use this electron pair to form bond with carbon. Therefore, carbon bromine bond will break. So therefore, you will get the product. This product in the middle, we have something called it's straight away one step. So we have something called transition state. Transition state is like this. So you can clearly see that carbon bromine bond is breaking. So nothing happened to this CH2, CH2, CH3 group. Nothing happens to this hydrogen. Nothing happens to the other hydrogen. But carbon oxygen bond is forming. This is transition state, somewhere in the middle. And you can see that minus charge on oxygen atom is disappearing. Minus charge on bromine atom is appearing. This is what you call transition state. Transition state. So because of this transition state, what we get here is, then you get the product. You get carbon, hydrogen, hydrogen, OH, CH2, CH2, CH3, then bromine has come out, right? But if you go for the next molecule, 2-bromo 2-methyl propane, it will undergo SN1 mechanism. But you can say 2-bromo 2-methyl propane undergo SN1 mechanism, right? So if you take 2-bromo 2-methyl propane undergo SN1 mechanism, this is what happens. This mechanism will take a 2-step. One is the slower step. In the slower step, what will happen? Leaving of Br minus ion and forming intermediate carbocation. So in there, what will happen? So we have the molecule. So here we have bromine. Here it is CH3 group. This is CH3 group. This is CH3 group. So first, what will happen in the slow step? This carbon bromine bond will break. Plus delta, minus delta, bond breaks. Where bromine get the both electrons. So what you get here is, you get the intermediate carbocation. So we have CH3, C, CH3, CH3 plus charge. So this is what you call intermediate carbocation plus Br minus ion. When the second step is very fast. Why second step is fast? Now is the attraction between intermediate carbocation and the OH minus ion. So we have CH3, C, CH3, CH3 plus OH minus ion. OH minus ion will lose its electron pair and donate it towards the plus charge this carbon atom and will form the bond. So therefore we will get the product. We will get it CH3, CCH3, CH3 and OH. So this is we have product. So this happens in 2 steps, but the first one have take place in 1 step. If you have right answer like this, then you can get full marks. Okay, in part B it says that an initial rate method may be used to investigate the kinetic of the reaction between hydrogen peroxide and iodide ions in acidic solution. The equation for this reaction is shown. H2O2 react with I minus ion with the presence of H plus ion gives you I2 plus 2H2O. The reaction mixture contains a small amount of thiosulfate ions. We know why we add thiosulfate, because when the iodine is produced, thiosulfate going to react with that iodine, which reduce the iodine back to iodide ions. The equation for this reaction is shown. Okay. As soon as the thiosulfate ion used up, the iodine that is further produced. So that means still thiosulfate ion is there. This iodine can't do anything. But when the thiosulfate is finished, the further produced iodine react with starch. Alright, we have starch in the system and results the color change. So when I see the color change, I know that there's enough amount of iodine has been produced to neutralize the thiosulfate sample I have added. Why we do this one? Because this iodine production is really fast. So if I don't have this thiosulfate, what will happen? With no time, the iodine will give us a color change. That's not enough time to measure. That's why we try to delay the observation by adding thiosulfate. Right. The time taken for this color change is noted, and the reciprocal of this time is used as the measure of the reaction time rate. That's another thing. If two vehicles are going from point A to point B, both has to be go from point A to point B. So it's the same distance. So that means if I want to compare the speed of these two vehicles, let's take one vehicle goes with 1 hour, second vehicle goes with 2 hours. But since they are traveling the same distance, I can assume that this time tells you which vehicle is fast. I can tell the vehicle which goes with 1 hour is faster and is roughly twice faster than the second vehicle. Why is that? Because second vehicle takes 2 hours. So how can I tell it? I can simply say that if I take this vehicle as X, this vehicle as Y, speed of this vehicle is equal to distance divided by time. Distance we don't know, but it's a constant. So therefore I say that distance is a constant divided by time 1 hour. Speed of second vehicle Y equals distance divided by time. Distance is the same, divided by 2 hours. That means reciprocal of the time tells us an idea about the speed. That's what the meaning of that one. But for that, we have to make sure that both vehicles travel the same distance. So that means we have to make sure that the color change is appeared when you have fixed amount of sodium thiosulfate in the reaction mixture, because then the amount of iodine produced to give the color change is the same. The result from the series of experiment was volume of the hydrogen peroxide was changed in given timetable, given in the table. So volume of hydrogen peroxide is different, but the volume of thiosulfate will be the same. So different volume of hydrogen peroxide, the reaction rate is given. You can clearly see that the rate is increasing when you increase the volume of hydrogen peroxide. And also you can see, like, when you increase the volume of hydrogen peroxide by 2 times, rate also roughly increase by 2 times. 0.9 become 1.8. Let's see. Give the color change after all the thiosulfate is used up. Color change, all the thiosulfate is used up, is iodine with the starch indicator. Iodine with the starch indicator will give you, first solution is colorless. When starch indicator react with iodine, you get a blue-black color. So that's the color change for this reaction. Then they are talking about part 2. Plot a graph of reaction rate against volume of hydrogen peroxide. So when you plot the graph, so here we have reaction rate, here we have volume of hydrogen peroxide. It should be a straight line which goes to the origin, and there will be one point will be an outlier. Volume of H2O2, when it is 30 cubic centimeter, there will be an outlier. Okay, see what are the marking points? Label axis with units, right? So when you are labeling, you put whatever those axes and put the units. Remember that one. Plotting the point straight line. Remember these, each and every point individually they are going to check in. Inside the graph you can use the pencil, right? But for these axes and the others you have to use the pen. But inside the graph you can use the pencil. Scale ensure points cover half of the graph paper. So remember, when you are using the scale, it should at least cover 50% of the graph paper. Minimum 50%, right? So you have to have minimum 50% of the graph paper should be used. Now here is very good. Like, so almost around like 75% to 80%. right? State and justify the reaction order with respect to hydrogen peroxide using a graph. So I can see this is a y equals mx graph. No, what is, so y equals mx. What is y? Rate. M means a constant. X means volume is directly proportional to concentration. No? Concentration of H2O2. R to the power 1 I can see, like, so can you see, it's like it's a straightforward, so that means I can see order of this one is 1, or you can say that rate is directly proportional to the concentration of volume. So therefore we are expecting a first order reaction, first order, because straight line graph, or you can say that rate is directly proportional to the volume of hydrogen peroxide used, right? Right, if you go for section C, the continuous monitoring method was used to investigate the kinetic of the reaction between magnesium and sulfuric acid at different temperature of the reaction. Equation for the reaction is shown. Okay, so volume of hydrogen and time. Okay, they have given volume of hydrogen over time. The graph show the results of an experiment at 80 degrees. Calculate the reaction rate at 15 seconds using this tangent given. So how do you find the rate of a reaction? Rate means change in concentration divided by time taken, right? So what we are going to do is at 15 second, now they have done the tangent for you also. 15 second is somewhere here, they have done a tangent. So if I find the gradient of this tangent, so what is gradients? When you find the gradient of this tangent, we have to take delta y, right? So delta y is the concentration change or the volume of hydrogen produced, and this one is the delta x. So if we divide delta y by delta x, actually I will get the gradient of the graph. Gradient of the graph in concentration versus time graph is equal to the rate of the reaction. So that means we are going to find the rate of this reaction. This concentration will come in cubic centimeter, time will come in seconds. So my rate will get an answer of cubic centimeter per second. So when I find the value, they are expect you to find a value between 1 point somewhere around 1.8, because they have given the graph, so it should be 1.8. They have allowed even 1.9. Unit should be cubic centimeter per second. So you simply select any point on this graph, any 2 points, then you find the delta y value, then you find the divide by delta x. So delta y divided by delta x will give you the gradient that equals to the rate of the reaction, right? Part 2, the temperature of the reaction was changed to 75 degrees Celsius. Now 80 degrees becomes 75. So you have to know that when it becomes 75 degrees Celsius, the amount of products won't change, but the reaction will be slower. Slower means less gradient. Less gradient means less slope. They will reach the same point, but little bit slowly. They will take more time, but for the same point. Alright, they will take more time to go for this completion. So when you see this straight line, we know that's the completion. So in the first time to go to completion, they use around like 60 seconds. But second time to go completion, they might use like 80 seconds. So we have to show that they will use more time to go for the completion, or like graph with less gradient. Okay. So that's the same thing they have drawn here. They're asking, draw a line on the graph to show the possible result. This was the only change. They did only change the temperature. They didn't change the amount of reactor. So therefore amount of product produced should be the same, right? And they're asking justify any similarity and the difference of the lines. So one similarity I can see is they will produce the same amount of product. It's because the concentration remains same. So at the end, they will produce 70 cubic centimeter of hydrogen at the end. That's the similarity. But the difference is this, the second, the one with lower temperature has a slower reaction rate. Therefore, is the line will appear below. You can say line with less less gradient, or you can say which is the one it will go below this one, and it will have slower reaction rate, because the reason is we are using low temperature. Remember, when the temperature lowers, the rate of the reaction decreases. That's what happens there. See, if you go for question number 19, they're asking many effervescent products such as vitamin tablets are solid which contain citric acid, C6H8O7, and sodium hydrogen carbonate. Only when these tablets are added to water is fizzing observed. The equation is shown for the reaction is equation for the reaction is shown. Okay, so we have citric acid and sodium hydrogen carbonate. Okay, so vitamin tablets, you get water, carbon dioxide, and sodium citrate. Give two reasons why this reaction is thermodynamically feasible when consider entropy of the system. That's so easy, because obviously you can see on your product there's a gas. So gas is produced, and also you can see there are more particles on the product side. This side we have 1 here and 3 here, altogether 4 particles here, but this side 3 plus 3 is 6, 6 plus 1 is 7 particles. Number of particles are increasing, and there will be gaseous product. Then obviously entropy is increasing. Gas and are produced from solid, more moles in the products than the reactor, so increase the entropy. So it's so easy. Those are the 2 points you have right. Part B. Describe in terms of particles involved why the reaction does not occur until the tablets are dissolved in water. In terms of particles involved, why the reaction does not occur until the tablets are dissolved in water. So you can see both these are solid particles. Actually, a reaction to take place, particles should collide with each other. When they are solid, we know that particles are in a fixed position. They can only vibrate. So if you take two solids, they are in fixed position, they can only vibrate. So the reaction between them is minimal. But when you dissolve them in water, particles will be able to move here and there. So we know that liquid particles, when anything is dissolved in water, in liquid, particles can move here and there. When they can move here and there, they can collide with each other. That's why they become feasible of reaction. In solid, particles are fixed inside the lattice, so they cannot collide or react. But when dissolved in water, particles are mobile. Therefore, reaction can take place. Those are the 3 marks they are expecting. You have to tell that in the reactor they are in solid particles cannot move. Then you have to say when you dissolve in liquid, particles can move. That's how we can do it. Then if you go for question number part C, in question number 19, for the reaction 25 degrees standard is entropy change of surrounding is entropy change of the surrounding is given. Calculate the enthalpy change of the reaction. We know that delta S surrounding equals minus delta H divided by absolute temperature. Delta S surrounding is given. So you can see they have given joules per Kelvin per mole. So therefore your enthalpy change will comes in joules per mole, right? And your temperature is 25, you have to add 273 to make to Kelvin, because they are asking absolute temperature. So therefore delta H minus delta H equals, simply take the entropy value delta S surrounding multiplied by absolute temperature. Delta S surrounding is minus 234.9 multiplied by 298. When you do this one, your answer will be minus 1234.2 joules per mole. That's minus delta H. So you know that you can multiply both sides by minus 1 to remove this minus sign. Then your delta H will be 70,000.2 joules per mole, or you can convert into kilojoules. 70 point zero 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 sorry 70,000 or 70.000, yes, 0.2 into 10 to power No need kilojoules per mole, or you can just simply write 70 kilojoules per mole. 70 kilojoules per mole. That's your answer, delta H value. And from that, you can get the answer for section C. Then section D, the enthalpy change of solution of sodium hydrogen carbonate is plus 18, is an endothermic value. Sketch the enthalpy level diagram for the relation between the enthalpy change of solution of lattice energy and enthalpy hydration of the dissolving of sodium hydrogen carbonate in water. Okay, first I'll show you the enthalpy level diagram. I'll show it here. Right. They are talking about dissolving of enthalpy change of solution of sodium hydrogen carbonate. Okay. So if I take solubility of sodium hydrogen carbonate means sodium bicarbonate. So this is sodium bicarbonate NaHCO3. When you dissolve in water, you get Na plus and HCO3 minus. Right. So this enthalpy change is given plus 18.6. How it happens? First you have to break this lattice. So this solid ionic lattice, you have to break it, forming sodium plus gaseous ion. Sodium plus gaseous ion and HCO3 minus gaseous ion. So breaking lattice is an endothermic one. Making lattice is exothermic. So upward arrow is, if I take the lattice energy, actual lattice energy is defined for gaseous ion combined and forming, this is delta standard lattice energy. Formation of the lattice, but here I'm talking about breaking. So that means this is now lattice energy is backward arrow. That means it is minus lattice energy. So remember, forming a lattice is exothermic, breaking lattice is endothermic. So it should be an endothermic value. So I can put it our sodium hydrogen carbonate somewhere here. NaHCO3 solid. And the first, that's my reactant. First, what I'm going to do is, I am going to break this lattice. Okay, so break this lattice. That's what I'm going to do it is minus delta H standard lattice energy. So I'm going to break this lattice and I'll get sodium plus gaseous ion plus SCO3 minus gaseous ion. Right. So I have the gaseous ion. Then what we have to do is we have to take this gaseous ion and add water. When I add water, what will happen? They will start hydration. So there will be hydration, delta standard hydration of sodium plus ion plus delta standard hydration of hydrogen carbonate ion SCO3 minus. Both ions will hydrate. Hydration enthalpies are exothermic. So what they are showing here is, but the overall is a plus value. So therefore, even if I hydrate them, my final aqueous ion should stay a little bit on top. So therefore, here we have sodium plus aqueous plus SCO3 minus aqueous. Why they should stay above the sodium hydrogen carbonate? Because there is a solubility of this one is plus 18.6. That means this value should be plus 18.6. Therefore, if I talk about hydration of these gaseous ions, so hydration comes downward. So here we have delta standard hydration of sodium plus ion plus delta standard hydration of HCO3 minus ion. So this is the type of diagram that they are expecting from us. Yes, that's the one. So delta standard solubilities, that's how it comes. So 18.6, that's equal to delta standard. This is delta standard solubility of sodium hydrogen carbonate.